Welcome everybody. Today we are going to discuss the homework assignment as always to give you some guidance and some tips on it. I'd like to move into hash tables, start discussing the importance of those, how we do them. Hash tables are fun, depends on your definition of fun. And we give you lab time. I will have a quiz that will be coming out the door this evening, so look for a new Chi Tester quiz. Also, I caught a cold last week, and it's been a very strange cold where even though the rest of the cold goes away, my need to cough keeps getting worse and worse and worse. So if I get into coughing fits, I might have to end this lecture early. I'm sure that disappoints all of you. All right, let's start. Questions for me.
I guess I didn't quite understood on the homework assignment. It was like so the operator. I guess there's some lecture last time. The operator star, operator plus.
Yes.
That's all on lecture. Okay, so on the pointer to the right, off the right cliff. So you just want us to be able to have it has to go beyond the end of the linked list by one.
It acts as if it goes past the last nodes, but you definitely don't want to go. If you try to go up past that node and do something like a pointer equals pointer link, that pointer will become null pointer, and you have lost the link. You'll have lost the list.
Okay.
You good so far?
Yeah.
You always need your iterator's pointer to stay on that last node. Don't move it forward.
Okay, so I'm just trying to figure out how to do that without.
Well, it's a simple. You do a simple if statement check. Do an if the pointer's link is null pointer, then you know you're at the end. So do a quick if to check, should I go ahead? And if it's null pointer, don't actually go ahead. Instead, for that if statement, you would set off the right cliff to true.
Okay.
Otherwise, you'd set it to false, and you'd actually move it ahead.
That I understand that. That's there's no pointer off the right link, so it's true. My question is, how do we move it back one if we go off the right cliff?
You don't. So you're saying what if an operator minus minus is called?
Yes.
So that one is if off the right edge is true, you're simulating being off the right edge. So you wouldn't actually move the iterator. You wouldn't move the pointer backward a spot. You would instead simulate going back a spot by flipping that Boolean from true to false. In other words, if I had, say, 5 nodes, we'll do it with 4 nodes here. There's links between these. These are just a very simple idea of nodes. Does that make sense so far?
Yeah.
Here you would have an iterator which points, but its Boolean would be false. Here it would point, its Boolean would be false. Here it would point, its Boolean would be false. Here it would point, its Boolean would be false. There is another state where it still points, but its Boolean is true. Does that make sense? So in a list of 4 nodes, your iterator could be in one of 5 states. And so how do you go backwards? Do you actually move the pointer back a node?
No.
Do you actually say pointer equals pointer backward?
Well.
No, you would just say if it's true, you just flip it to
true.
false.
Yeah.
Otherwise, if it's false, what do you do?
Move it back.
Move it backwards. You got it?
Yeah. Just want to make sure. Just want to make all the other ones made very easy logical sense to me. This one.
No, this assignment and the hash table assignment tend to really eat students up. Is because if you can get lost in the weeds and the details. That's a good question, though. Other questions? I did run across one homework assignment. No, Jacob, the code from the June 5th lecture was one of the song numbers. So I did have a homework assignment tip. Someone came in. They had a strange error message. It dealt with iter swap. I've seen these before. I usually get a handful of them. The student was trying to use iter swap, and it was complaining inside of the iter swap code, not inside of their code, but it brought up a compiler message elsewhere. And the reason is that it traced all the iter swap was trying to dereference the iterators, use the operator asterisk on those iterators, and it couldn't. Long story short, the student's operator star had a return type of T. That's returning by copy. You can't swap if you only have copies of the data. So you need to make sure the operator star's return type is T-reference. That allows you to have an actual reference to the data, and then it makes it modifiable. So just make sure in your operator star you have a T-reference. Other questions? Yes?
I'm just confirming on the code, it's supposed to compile without any errors when we just download it and
I think so.
right?
Did it not?
I have 79 errors and I haven't even
Well, you know what those errors mean, right? Well, I showed you somebody had a t-shirt about this,
Yeah.
but it's a Google fix all my mistakes. No, images. No. What, do I not have it here? It's the old joke that I can't seem to find it. You know the 99 bottles of beer on the wall. Take one and you keep counting down. Instead it goes 99 compiler errors. Fix one, 137 compiler errors to go. It seems to always get worse. Find the top one, work on it. Did anybody else have problems with it? Did you download it? Did it compile first run?
No.
There's a bug in there? Uh-oh.
You just have to add the beginning and end.
Oh yeah, it's not compilable for that reason.
Oh, yeah.
Because my test code wants a begin and end,
Uh-huh.
and I didn't. This is one of those assignments where I wanted you to supply it. It was tricky. I know I want all my assignments to compile right off the bat, but I don't want to give things to you, and this is one I really wanted you to do yourself.
Okay.
All right, other questions? These have been great so far. You could ask any question in the world. No, I better not. There's a great movie, Airplane, but I forget I always watched the TV version,
Yeah.
edited version as a kid.
Yeah.
I forgot how crass that show is, but it's really, really funny. They have a help desk that cracks me up. People come in asking airline questions, and they start asking questions about what's the fastest land animal and advice about life. All right, so let's move on to hash tables. I like to start this discussion of hash tables by talking about a really fun idea for a supermarket. What if you go to a supermarket and you ask the store worker, hey, I'd like to get some milk. And they say that's down aisle 1. Say, all right, I'd like some batteries. That is also down aisle 1. Okay, I'd like some TV dinners. Hungry Man's are great TV dinners. They're down aisle 1. What else do you go to the store to buy? What do you need? Anybody need to go to the store tonight to get something? Electronics? That's down aisle 1. Yogurt is also down aisle 1.
Eggs.
Next, eggs down aisle 1. It's a very long aisle. The store is only 1 aisle long. Somebody found a big plot of land next to a freeway. It's about 1 mile, 2 miles long, but only about 50 feet wide. And they built a supermarket there. It's more of a gimmicky store. You go there just to take photos of yourself, selfies, put it on Facebook. You go shopping there for exercise. You go down 2 miles of aisles, come all the way back. It's a great experience. This is very much like an array. If you have a whole bunch of items and you want to go search up some item, does it make sense to just search every single item down in the array to try to find it? Well, if it's only 50 items or 100 items, is that really a big deal? No. But if it's a lot of items, that would be like shopping down at a store with one gigantically long aisle. Depends on your idea if that's fun or not. So what we need is a better way to start searching up our data. And how do stores organize their data better? How do they organize their inventory better? Do they do it alphabetically? That would sure make things interesting. No, how do they do it? They kind of try to, no, they don't do it by SKU. I mean, they do it by product. Where's my cereal? I don't know, maybe cereal all has a starting
Clothing,
SKU.
electronics.
But they say like our item, aisle 15 has this stuff, aisle 25 has this stuff. Because everybody needs batteries, Jessica. You just throw them out and people say, oh, I need some. So they've got a system in place and it seems to work pretty well. the aisles tend to be grouped, foods in one area, kind of kitchen areas in another stuff, and it does the job. Now, suppose it's not that I'm not trying to store, I don't want to look up items in a supermarket, but instead I want to start storing students, and I want to start looking up student information. Let's say, how many students have gone through, how many Weber State students have there been? Take just an estimate. All-time Weber State students.
Since the beginning of Weber?
Yes, since Weber State Academy. 2 million? It's probably much. 5K? It's a bit low, seeing that there's about, 20,000 students right now enrolled.
Well, there's 20,000 students enrolled. How long has Weber been there?
But yeah, I mean, but it hasn't been always 20,000. It used to be like a very small building. And it became a college with, like the old, now they finally demolished them, the Elizabeth Hall and the other new building, the physics building. Those used to be buildings A, B, C, and D, and that used to be all Weber State College, and that was it. Felt like a high school. Tracy Hall. And so, I mean, obviously it's grown. Let's say there's been 100,000 Weber State students. We'll estimate. I'll average the two of yours out. So we have 100,000 students, and I want to start searching up students. Should I put them in an array to find them? No. So what would be a good way for me to better organize or better search up students? Somebody comes to me and says, hey, I'd like to get my information my transcript. All right? They give you your name. Do we search down all those items until we find that name?
Three-dimensional array?
So let's start coming up with new approaches to find data better. No, you're not. This is not a class of saying buy somebody else's tool. This is a class where these tools don't exist. Nuclear bomb hit. We just built computers back from scratch, and you're the only smart guy left in the world, and your job is to build the data structure. That's what this whole course is designed around, for that one moment.
All graduating students or current students too?
You're the smartest computer science person on the planet. It is your job now to build a new data structure. How do we do this? No. We're doing, all right, Jan, what we're doing, you said dictionary. What we're doing is effectively a dictionary lookup. But you have to write the data structure for it. So, tell me design a data structure. You said 3D array. How does 3D array help us?
Well, instead of just having, now we have to decide on how we want to do it, but instead of just having one array with everybody name in it, one long list, we would have different people and different numbers for the array, and we can search by that array.
So you would do something like you would do it by dimensions. So what, like the first dimension would be what, like the year they graduated?
The year they enrolled or the year they graduated.
So let's say we do the year here.
Well,
Then
I guess the first thing would, are they currently enrolled or they graduated?
So you would do like status in the first dimension.
Yeah.
All right, then what?
Then I would say year enrolled.
Okay, and then what? And then when you do last name, first name?
I would probably do like last name.
Does this help? Will it make it faster?
Make it faster than just normal, right?
Are we already off to a good start? Yes. The nuclear holocaust is getting better. The effects of it, we're getting out of it. Still not back to where we need to be. But status, enrolled versus not enrolled. If you say enrolled, that automatically kicks you to maybe, say, 20%, 10%, or whatever of all existing students. All right, then they say year. All right, there's been people here I've seen people going back to the 80s who were getting their degree done. So not everybody is enrolled in 4 years. So you might cut that down by another 90% based on the year you're here. So only 10% of that left. Then what? Then by last name, you could start saying, all right, here's all. But the problem is you're going to have a lot of last names.
Yeah.
So you might say, where's the Smiths? Where's the Johnsons? Where's this? So you might have a lot of data in that last name column. So your array might be very big and messy. So for example, status will need a total of 2, enrolled or not enrolled. There might be other statuses. Year, let's say we do go all the way back. Let's give ourselves room for 150. And then how many last names are there?
1,000.
I think there's more than 1,000. So let's say that there's been 10,000 different last names. All right, so you need an array that's 2 times 150 times 10,000 elements, which is a lot of data. I should be able to do this, but I can't think at the moment. 3 million items, that's not so bad. Now you say, all right, well, a student record takes up, a kilobyte. You're now at a megabyte for your, or a gigabyte, 3 gigabytes for your student record table. That's not terrible. It fits, but can we do better? How can we do better?
Could you use structures in a very similar way as far as these, as far as the 3-array system?
You tell me.
I think you could do. I think
As
you could
part of
do
this
a
nuclear
structure and
holocaust,
then-
I died. So you gotta.
So we could use student's ID number instead of last name.
You would do an ID number.
Well, I'm just saying, an ID number would be a unique identifier.
That helps. What else do we have? I saw another hand up. Nope, no, you were just yawning. So if you do a W number, though, how does that help? Would you put the W number? I mean, how do you work with that W number? Someone says my W number is 1, 2, 3, 4, 5, 6, 7, 8. Now what? What do you do with that?
Well, we could put, it's a way, a unique way, so instead of having 100,000 array, you wouldn't need that so many array because you could put it by year and state, but then you could look through by W number, which would reduce the search radius because you don't have to multiple last names.
All right, that helps a bit. Keep going.
It's like you're saying, because with last name, you know, like 50,000 payroll balances, but a W number reduces that redundancy, right?
So how does it reduce the redundancy? So instead of 10,000 last names, how does a W number? How many? So you're saying do a W number for this third dimension here. What? So how many W numbers? What's the size of this dimension? Is it just going to be 1 here?
No.
How do you use the W number to your advantage?
Okay, so the W number,
No, I was gonna say something different, go down a different track.
All right, we'll come back to it. How do we use a W number to our advantage?
well,
Divide it into chunks. That's a great idea. So how would you divide it into chunks? 10. Or an easier way is just look at the last digit or the first digit. And that can tell what chunk it belongs to. Does that make sense? That way you don't have to worry about trying to keep your chunks all equally sized. You just make it easy. It's kind of like, I always hated when they did this, separating people out by last names. Actually, it worked nice for me. You would hope that if you say, all right, well, let's split up, there's 26 letters, let's give everybody 6 or 7 letter groups. So what, A through G? And you find out that half the population seems to be A through G. And those of you, who of us have like last names like P or beyond? And you find out, it's really nice, isn't it? It's like, hey, there's none of us. Or unless they do things alphabetical order, it takes forever to get to you.
Like all of them are Z.
But it doesn't, the last names aren't well distributed in that way, but W numbers, we hope, are well distributed. Are they well distributed?
No, we assign them. Yes.
How do you know? It turns out that that a lot of numbers that look like they're well distributed, like you might say, you know what, let's take a look at the last number of everybody's W number. And you might find out that for whatever reason, the 3 just never was supplied to anybody. And so it kind of hurts your plan a little bit more. And I've seen people go down this road. For example, I've seen people go down the road of saying, what if you were to divide everybody into also by, let's say, the first letter of their last name? Will that give us good even distribution? Why not?
because, like you said, the majority of the population is through A through G.
What do you think? What letter, last name, the starting letter is the most common? Just take a wild guess. S. All right. What letter last name do you think is the least common?
Z.
Z, X,
X.
Yeah, X.
X. Let's find out. Well, this is answers.com, which is definitively correct. United States. S is 10.93. That does appear to be the best. X is 0.02. So if we try to distribute everybody by first letter of last name, will we have good distribution of data? No, the person with an X last name, we find him usually really fast. Somebody with a Smith, they're going to be looking a long time. Does that make sense? So another strategy I've heard is people get more creative and say, let's do the last letter of the first name. Do you think that distributes it out better?
No?
Why not? Alexander's saying no, no, no. Why not?
Because most names probably end with a consonant. I don't know. It's even worse than the last name, I think.
How many last names you know that begin with end with a Q?
Ah. So I got a graphic here. I'm going to reload. Come on. Here we are. Distribution of last letter in newborn boy's name by year. Zoom in a bit. Do we have good distribution?
No.
It's even worse.
X is a little better.
Oh, wow. Oh, geez. Yep, there are.
Isn't that crazy?
Yeah.
I had no idea. It's like, what? I was thinking, like, that's weird. And I started going down my kids' names. It's like, I named my boy with an N on the last name. Like,
Mine too.
did society somehow get to me and I had no idea? I thought I was trying to... It actually made me paranoid when we had our second boy. Oh, I started floating names, and I was just in the back of my head, that ends with an N. We can't do it. We have to rebel. Why? I'm not going to tell you why. It's a petty reason. So would this be a good approach?
No.
No. So W numbers are a little bit better, but you hope that those numbers have decent distribution. But that may not always be the case. And there's one great example I know of this. It was, 10 years ago. There's I think it's fair to say they're a very partisan, a team-based, hyper-partisan website, Daily Kos. And they paid for another group to be a poller. You know, there were 7, 8, 10 polls, major pollsters at the time, and they wanted to be one of these major pollsters. So they had their name slapped with it. They paid this entity to go poll nationwide feelings of approval, disapproval. And it wasn't until, I believe it was the 538.com folks, said, one great way that you can tell if numbers are really random is looking at the distribution of the last digit of the data you get. And so they took all the surveys, all these approval number surveys, and said, let's take a look at all these last number digits. And sure enough, almost all of them were great. Yeah, these are well distributed. These look great, except for the Daily Kos poll, that they were definitely not well distributed. There were some numbers that were coming up way far more than others. Why do you think that is?
People made the numbers up.
Because people made the numbers up. So they paid this company to go poll. The company said we'd do it, and some guy or some person just made up numbers and sent them back. And this went on for years, and nobody caught it. And finally, the Daily Kos people said, we're going to get back to we're going to find out why. And the company says, we'll get back with you, and then they shut down.
Now, could you do by date of birth? Or day of the year of birth? So
Is there good distribution on dates of the year?
I think so.
You get better. So we get to this, we're getting in this debate of how do we get good distribution? Do you see, why do we want good distribution to begin with?
So there's not.
So that everybody kind of gets a fair shot to get their data found, correct? We don't want, not just for fair shot, we want to make sure that we don't have one array massively bigger than another array, or whatever we use to store it, we don't want it to be massively larger. We want to try to have all of our data have roughly equal lookup times, correct? Distribution is the goal. So this is the goal. Let me write this down because it's important. Good distribution is vital. Now we've come up with some systems. The best one we had so far was W number. But do we know if it's actually well distributed? Can we guarantee it?
No.
Could we start to analyze it and get a good feel if it's well distributed?
Yeah.
Could somebody down the road change it so it becomes not well distributed 5 years from now?
Yes.
Yeah, so for example, if you were to go not off the last digit, but say off the first 3 digits or first 4 digits. Initially, W numbers were assigned numerically. Students, as they came in, all right, you're the next student, you get the next W number in line. So we would have had a whole bunch of W numbers starting with 0000. So it's the best so far, but we can't guarantee or promise it will stay. We can't promise it will stay that way. You can try to say, well, this will be our policy. The data guys are telling the administrator folks this is the way it needs to work. I can tell you in any institution that communication always breaks down. So are there any other better plans beyond this?
Like assigning a number.
No, we were assigning a number. But what if somebody comes along and says, I want to assign this way? My daughter's favorite number was 3, and she died. So now everybody's W number will end with a 3 in her honor. That doesn't help us.
What about, male, female?
That doesn't help us much either. In fact, there's more females than males in universities now. A much larger number.
Like, it's not even close to.
It's like 60-40 now, I hear. Does anybody know the exact numbers on that?
I mean,
It's not in computer science, unfortunately. We're getting those numbers up.
Yeah, I see.
You have 2 in here. We're getting there. We have 1 online. No, we have 2 online. No, we're getting there. It's a side rant. I was so mad. My daughter was into bugs and science, and she loved the movie Cars, and she went to the first time taking her to a store to get her some kind of Disney memorabilia. She loved the movie Cars. She watched it all day. And you go to Disney and say, all right, where's the car stuff? And it's definitely geared toward boys. So, well, is there a single item that's a Cars memorabilia for girls? 0. So we went to the girls section. All princess dresses. It's like, this is why you have. How many 7th grade girls say, what do you want to do when you're an adult, when you grow up? How many of them say, I want to do computer science? I want to be a programmer. Yeah, I know. We have a few of you here, but it's getting better. But that's the reason why. It's just.
It was marketing to begin with. That was the only reason that happened.
And then you go look at the education department, and it's the exact opposite ratio. I really feel like we should just get our 2 departments together and start doing trades, like elementary school picking teams. I'll trade this guy for this person.
No, question. How many male kindergarten teachers do you know?
Not many. It's the exact problem. Anyways, side rant over. Any other better ways to distribute our data?
So
Well, I guess we could do like the day of the year they're born.
No.
So the problem we're having is every time we have we're having to extend ourselves and really get creative. What about this? What about that? What if I have to start storing various kinds of donuts? Do you want to manage your donuts by year? I mean, it doesn't make sense. You start having to come out, well, we can do by sprinkles and percentage that are chocolate. You don't want to have to analyze your data to try to grab some well-distributed feature out of it. We want a better solution.
We could hash tables.
What are hash tables?
Hash tables are you put in like you put.
We're going to get to it.
So when we get to it, yeah.
That's right, Jessica. No social security numbers. Nuclear war.
Do you ever call it, but you don't have a government?
It's voluntary.
it's social. It's the social security number.
All right, so I'm going to show you we'll do MD5 to start. Nah, we'll go straight to the good stuff. I need to update that. Mathematics has given us, and computer science has given us this great thing called a hash function. It's a one-way function, and you know what a function is in math. It's reliable. You give it an input, it always gives you the exact same output, correct? It doesn't change. Just because it's a Tuesday shouldn't give you a different output. The idea is that we give it some input. In fact, I think hopefully there's some code. Here we go. Here is the SHA-256 algorithm. You give it some code, and it starts applying all sorts of weird bit shifting, bit rotations, XORing, looping it over, and just basically mucking up your data. It's in such a way that it just keeps rearranging bits, multiplying bits, anding, oring bits, doing stuff with bits, looping this over and over and over again. And when you're done, you have the set of bits that you can't understand where it came from your data. And because you're doing rotates and shifts especially will lose your data, you can't undo it. It's almost like if you take a cow, you can turn it into a hamburger. But can you turn a hamburger back into a cow?
Or the right DNA slicing and the.
No, the original cow, not. And so hash functions work the same way. You take your data and you muck it up in such a way that you get this output. And I know it's a bad analogy, but it's like if you were to take a cow, let's say you cloned it, so you have exact, perfectly precise twin cows, or some Star Trek cloning machine, they're exact, and you muck it up and you get the exact same hamburger out every time. You following so far? And what you do with it is that you don't take all the bits, you usually just take a good chunk. In SHA 256, you end up with a chunk that's 256 bits long. So for example, let me show you how this can work. Let's hash somebody's name. Who wants to be hashed?
Hash me or not.
David. Let me,
Free potato, so.
hold on if I can, web page generator. There we go. So we'll do David, calculate the hash. Here you are. I'll put this up in Notepad for you. All right, and we will do Jessica, calculate hash.
Now, take the capital off Jessica.
Let's do the alternate spelling of Jessica. Can you see that? Those numbers all right? Do you see any kind of pattern between the two Jessicas?
No.
They've been mucked up so well that you can't see, and that's the idea of these hash functions. They should be mucked up so much that a single bit changed in your input should completely change your output. Let's do a couple more just to get a feel for it. We have Manny. Throw Manny in there. Where do I go?
Now, calculation will also change that, because let's say you put it in all caps.
Lowercase Manny.
Now, if you were to do it again, does it come out with the same thing?
Yeah, that's really important.
Gotcha.
Yes, it's not random. Hash functions have nothing to do with randomness.
Okay.
Does that make sense?
Yeah.
No, it doesn't have to just be a short string of text. Let's see the script to Monty Python. I'm sure that's online somewhere. Where are you at? Here we are. Can I plug this whole thing in there? Yeah, there we go. Monty Python script. Was that fast to compute too?
Yes.
Yes, it was.
Now, that's the whole script right there.
Yeah, so here's the great part about it. Every time you get it, you get the same hash. What if somebody goes in there and wants to change one of these jokes and, oh, here's a typo. Well, let's see, where are we at here? Do we have a typo in here? This isn't Monty Python. The album of the soundtrack of the trailer of the film of Monty Python.
This says everything but.
I think that's the point.
Yeah.
That's awesome.
I think
So let's say that you put a space in here, okay? And you recalculate it. What happened? Completely changed. Now this makes hash functions it's this fantastic tool where I just showed you the basic idea. Take a whole bunch of data, throw it to this function, you get this 256-bit mangled up output. Can you undo it? Can I take this output and undo it to get back to that script? No, I lost stuff along the way. But is it always reliable? If I put that same script in, will I get the same output out? Yes. And because it's this reliable process of giving you this mucked up, a single bit can change it dramatically, it gives you a number of very useful tools and features. Cryptography uses it all the time. We'll use it for hash functions. It's used as a data fingerprint. For example, what if somebody says, hey, I'm gonna send you over the internet this script, and when you receive it, the hash of it, I already told you or maybe you tell them on the phone, the hash of it should come out to this. Okay, so then you receive it, and then you hash it yourself, and you compare hashes. Does that give you a very good, reliability, integrity to let you know that this script is what the original script was? Nobody tampered with it.
Yeah.
Yes. If they tampered with a single character, what happens?
Completely different.
Correct. So this gives you a great way to check, have things been tampered. It's also great, even, for example, database or backup systems. How do you know if you're backing up the same file twice? What you do is you hash a whole file, and then you just check your file and say, well, what is this? I've got this hash for this file. Do I already have that hash somewhere in my system? Does that make sense? Helps you very quickly find duplicate files. Even if you rearrange and put files in different directories, it just has to back up files. How can hash functions be useful for us in our distribution problem?
You can make a lookup table.
Each person has its own hash, and you just take a certain number from the hash to.
So every person has. So let's say I ask for your W number, and you say it's 1, 2, 3, 4, 5. What do I do with that?
You throw it into a hash, and then you just take the last.
All right. So I take W 0, 1, 2, 3, 4, 5, 6, 7. That's a syntactically correct. And there's your hash function. What do I do, or your hash value? What do you do with that value now?
Take the last 4 digits.
Take the last 4 hexadecimal digits. Now what? What was that? Why would I take these 4?
No, you can.
No, tell me what would be the benefit of taking these 4?
Or if you chunk the whole thing up, then you can just separate it out and do it
You're overcomplicating it. It's even easier.
Yeah, no. Just associate them and look them up.
Let's just say I just use that digit. How many possibilities are there for that last digit?
Well,
Okay.
No, a hexadecimal.
16.
Correct. So what can I do with those 16? If I know there's 16 options, do I have good reliability that there's well distributed, a good distribution in that last digit?
Yes.
Yes. That solves a distribution problem. In fact, let's back up a sec. Does it solve a distribution problem for almost any kind of data that we have?
Yes.
People, donuts, products. I just find some data. I don't care how, even if it's mostly the same but it's off by a bit. I throw it into a hash function, get a nice well-distributed output. I take the last digit. What do I do with that last digit?
You compare. You put it into whatever.
I have 16 possibilities, so what can I do now?
You put it into whatever 0 to F, and you put it into that file.
So you're going to make 16 files, and say, and so
16 tables, and each table has its own.
so I would go to table 3 since this last digit was 3, and I'd insert, or I'd go, and I would hope to find the student record for that W number in that one. Correct? Does that make sense? How much now have we reduced our searching over a flat array? If I were to use just the last digit, how much faster?
12 times
Assuming well distribution of data. How much? 12 times faster?
16 times faster.
16 times faster. Because we've reduced it by 16. Can we do better?
We could do 2, which would
All right, so if I do 2, how many possible files or buckets or things do I need? Not 16, but how many? 256. That's getting pretty good. So let's go back to our Weber State original question. 100,000 students. Let's say we look up off their name, we have some system, uniform system we can use to look them up. And we hash it, and we take the last 2 digits and go to, say, one of 256 buckets or files or whatever, or arrays or whatever we use. How much faster now has our search become? What's 100,000 divided by 256? There should now be only about 390 or so students per bucket. Is an array search of 390 more reasonable?
Yes.
For a computer, yes, but could we do even better if we wanted to? How?
Another digit.
Another digit. Do you see the ease of this? Now how many buckets are in 3 digits worth? Should be 4096.
Yes.
All right, so I take 100,000 divided by 4096, and now how many students are there per bucket?
24.
24, is that better?
Yeah.
Can we do even better than this?
Take the last one.
Last 4. Now that's 65,000 buckets. So now you're having only like 1 or 2 students per bucket. And you laugh like, wasn't that overkill? Not necessarily, because look what we just did. Hold on, online students, make sure I don't ignore them. I'll draw this out. Here, there we go. And you know I got stuff here somewhere. Where'd you go? The idea is you take your data, and I'm gonna take some aspect of data, some identifying information, which I will call the key of your data. A W number is a common key. Doug.
You're referring to as buckets and the number of people in the buckets. Wouldn't you want your bucket size and the number of people being searched to be as close to each other as you can? Otherwise, you're over searching on one side.
No, because it well distributes your buckets. So if I've got 65,000 buckets, then on average, each bucket only has 1 or 2 students in it. So you don't really get lopsided. Was your question about...
Search was 65,000 buckets.
No, it doesn't search 65,000. Let me show you. You don't have to search 65,000 buckets. So let me get into this. You don't have to skip. It's even better than that. So we take a key. For now, let's think of our key being, say, a W number as an example. Sound fair? What do we do with our key? Hash the key. What does that give you? A hash value. What do we do with that hash value?
Take the last 4 digits.
Take some last digits. In our case, we're taking 4 hex digits. Correct? Now what? Let's tell us that in this situation, I take that number, it's in hexadecimal, so I go to my trusty calculator, which is not in programmer. I go to hex, pop it in. So I go to bucket 18,323. Sound fair? Go to that bucket. What was it? 18,323. Then what? Search that bucket for a matching key. And then do whatever you want when you find your data. Do you delete it? Do you return it? Do you update it? Whatever you need. Now, Doug, your question was more along the lines of searching. If you have 65,000 buckets, wasn't your complaint something like, well, now aren't you searching a lot of buckets? Correct? And I think another student said the same thing. Do we skip over the empty buckets? No, how many buckets were we searching when we use a hash function? 1 bucket. Do we have to look at the other buckets? No. Do we have to see if they were empty or not? No. How do we just search 1 bucket? We're able to jump straight to that bucket. right? This is like, imagine if we had now instead of my supermarket, my funny idea for a supermarket that was 1 aisle but 2 miles long, now we have the computer science hash supermarket. And you go there and it's not 12 aisles or 20 aisles, it's 65,000 aisles. And you say, I would like some extra chewing gum ice crystal flavor. And then they say, all right, well, let's just take what you said, let's hash it. Boop, 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 okay. It is down aisle 32,018. All right, and you walk down there, and in that aisle is only those pieces of gum. Wouldn't that be a great supermarket?
But you still have to
It'll probably be the same length.
Now, for us, going to bucket 32, going to aisle 32,018 is going to take a long time. How long does it take a computer to go to bucket 18,323?
It doesn't have to true.
That's what RAM is for. RAM is great on that. That's the whole purpose of random access memory. You give me any random memory address, I can go get to it at roughly equal time. Doug?
By that same token, why not just use the whole hash value and you don't have to search anything there?
Well,
You've got that.
You can't guarantee, though, that you... So you're saying, like, why have a bucket that could have 2 students in it? Why not make even more buckets and have only one?
If you use the whole hash number, it's 1 bucket for each individual.
Okay, all right, so you want to use the entire... These are great questions, Doug. I love it, because I would ask the same questions if you didn't. How many buckets could we have if we use the entire number?
You're gonna have a full list.
16 to the 250.
Well, yeah, let's find out. What is 2 to the 256? Wolfram Alpha, you'll save me. 2 to the 256 is... It's going to be a big number.
Wait, wouldn't that be 16?
There's 256 bits.
Oh,
So that's how many buckets.
Yes. So you would have 15 quadrivigitillion, or something times 10 to the 77 buckets. That's a lot of buckets. Would you agree, Doug?
Yeah.
Okay, just making sure. Just for fun, number of electrons in the universe. We could have... we have enough electrons to make this work. If we assign every electron a bucket, we can pull that off. Sorry, I'm just having fun.
Could you zero out the non-used buckets though?
No, what you do is you just get enough buckets. My rule of, it's your call as a developer, but use enough buckets that make sense for the computer you have. So if you, I know it sounds crazy, but we're not environmentalists with our computers here. If you got 16 gigs of RAM and nobody cares about the power bill, using your RAM adds a little more power. Use it. If you've got 100,000 pieces of data, why not create 100,000 buckets or 200,000 buckets? You don't want to really create 1 billion buckets. That's really overkill. But if you did 200,000 buckets, then it's going to be extremely unlikely that it'll be much more unlikely that some bucket will have 2 things in it. Most will be either 0 or 1. You might have a random oddball that gets 3 or 4. But now you have really nice fast lookups. Yes?
I think buckets would be 11 digits.
11 digits?
Yeah.
What's 2 to the 11th? 2 to the 10th is a megabyte, so it would be 2 million. No, that's not right.
no, 2 to the 11 is 2048, I think.
Yeah, 16.
Yeah, 2 to the 10th is a kilobyte.
And the 16 to 11.
So you want to use 11, but that's 11. Or you want 11 bits or 11 digits?
11 digits on
Okay, so there's 4 bits per digit. A digit's a nibble. It's not a byte, it's half a byte. It's called a nibble. $17 trillion buckets.
Is that reasonable for modern?
No. How much RAM do you have? Do you have 17 terabytes of RAM?
Maybe deep blue or something.
No, we're not going to do it. But you're asking good questions. Does that make sense so far?
So we want the amount of buckets to be within how much RAM our particular computer.
It really depends on the need of the problem. a good rule of thumb is, yeah, I mean, you don't need to just maximize your RAM, but I think one good measurement, a practical rule of thumb is if you can make the amount of buckets be pretty close to the amount of data you have, that'll make it nice and fast. But if you run into memory constraints, then just say, all right, then your next constraint is, I want my hash table to use this much memory or hard drive space. And that's your limiting factor. Yes?
And to be clear, the reason that we're going to have multiple things, or we can have multiple things per bucket is because some things are actually going to hash the same way. Like there's some data loss, so there's a possibility that there's going to be overlap, right?
You said data loss?
Yeah, like we said.
What do you mean by data
Well,
loss?
you can't convert it back, right? You can't take a hash and convert
Yeah,
it back.
I can't get that script back. So what were you getting at?
But there are, particularly depending on the function, multiple things might hash the same way.
You might have two, so you're saying you might have two names hashed to the same value? No, ho. No. Now, it's possible you might say if you take off the last 4 digits, that you will definitely, I mean, if you just take the last digit, you're going to get some of these that collide.
Yeah.
That's possible. But are you going to get entire hash functions? No. In fact, if you can get if you can find 2 different strings that hash to the same SHA-256 value, you will be king of the nerd world. You will break SHA-256, you'll make a lot of people really angry, and they will just have to go searching for a new hash function. This happened before. There was something called MD5. It was a very popular hash function for a long time. The problem is it wasn't a good algorithm, and people found ways to break it, in such that they found very quick ways to generate 2 different input strings, or they took 2 different files and got them to hash to the same output. In fact, I think SHA-1 was just broken. What does SVN hash function? Yeah. SHA-1 was a very popular one, and it was just broken recently. And there's code repositories. I don't know how to describe it if you've never used it. I treat them as code secretaries. Let's say 20 of you are working on a code project. You can all check out code files, make updates, send them on back in. And it keeps track of all these files and their changes by doing hashes on the files. And so that way you don't have to store the entire file. They just say, this file is represented by this hash. That way, if we have all these different files, we can tell if there's duplicates of the same file or not. And it used SHA-1 to manage it. Somebody broke SHA-1, found a way to get 2 different inputs to have the same SHA-1 output. So they had some fun with it and immediately went to somebody else's SVN repository and uploaded these 2 files to it. Crashed it. So we're going to use other uses of hash functions. They're great for passwords. What if David, your password was also David? You're being sneaky. Would I want to store a plain text password David in my database if I was storing your passwords? No, but what could I do to be a little more secure?
You could hash it.
I could hash your password and store that. What if my password, my database is leaked? Some hackers came in, ripped the computer out of the wall, took it home with them, and they look up the password data table, and they found for your account we have this password. Do they know your password? No. Can they reverse the bits to get back to your password?
No.
No. Could they reverse these and get back to that script? No, but guess what they can do? Lookup tables. Do you think David is a popular password? It's possibly been done. So I'm gonna put in that hash. Crack. I gotta put in a CAPTCHA. Is that not? Screw this. We're gonna go somewhere else.
Someone I know uses that if he forgets his own passwords.
Decrypt. That's better. Come on, come on. This is the future. Faster. Does it not have it? It has not recognized that one before. Oh, is it? Oh, there it is. David. So somebody has gone out and made giant databases of very popular, all combinations. That's why they want you to do bigger combinations of passwords, because if you did a 6-character, just straight plain text, somebody's gone through and generated every possible hash for all of the possible values. And it just takes a big database. You look up hashes and you can find it back.
Just for fun of it, let's just hash the thing. Mary had a little man. Come blow your horn.
Okay, that one I'm almost certainly not going to show up in these.
Okay.
That's a good password strategy besides saying, hey, let's make it 20 letters, mix of numbers, lowercase, uppercase, digits.
And that's not even my password.
Use it, if you did a phrase, then it's much harder to find that exact phrase. So for example, just we'll use Google as my database here. I need 4 words here. Somebody tell me a word, just yell out a word that you know, that you're thinking about.
Booyah, Grandma.
We have booyah. What else?
Smash.
Smash. Keep going. Other 2 words, please.
Nintendo.
No, that's related to Super Smash Brothers. Keep going.
Green.
What?
Green.
Green. One more.
Dog.
Dog. What's the chance that Google has this exact same phrase?
No.
It's not going to happen. And we had booyah pet dog with green. That's pretty good, but not the exact. So one good password strategy is to think of 4 words that mean something to you, not as part of a common phrase, and make yourself a really long password. It's easy.
So-
Yes?
Are we saying the hash is the actual password?
No.
You would store, no, what would happen is if you were to go to a website, for example, and put in your username and password, you don't even send the whole password across the database or across the network plain text. You hash it on the client side, on the phone or on the computer. You do a SHA-256 hash, for example, on the password there, send the hash across the wire. Anybody snooping just sees the hash, and then you compare the hash that they sent you with the hash you got in your database.
Gotcha.
Does that make sense?
Yes.
You can do more to it, like salts and whatnot. I'm not going to get into it in this class, but that's the general idea.
Okay.
It's also why you don't want to store. You have simply easily undoable hash functions. There's other things, rainbow tables, which takes this concept of chaining to a new level. But
Is there anything beyond the hash 256? Is there another one?
yeah, you can do SHA-512. You can do SHA-1054. There's other kinds of hash functions out there, but SHA-256 right now looks really. I haven't heard anybody getting upset about it. I remember 10 years ago, people were saying SHA-1. They think they're going to break it. They called it sharks swimming around a bloodied algorithm. Nobody could figure out how, but everyone could see there were flaws in it. And it took 10 years to finally exploit it. SHA-256 looks like it'll be strong, but we don't know. Maybe the NSA has secretly broken it and hasn't told anybody. That'd be pretty funny.
So who builds these algorithms?
You remember my nuclear analogy that
The smartest.
the smartest guy in the world did it? No, it's really just some computer researchers just said, let's try mucking the data this way. And they learned. The first time they mucked it, someone said, well, here's a flaw. So they mucked it this way. They learned better. There's a flaw. Let's muck it this way. And so as they get better mucking up the data, they start to learn what tricks really work and what tricks don't. And as you saw, it was a pretty... Did I have it here? I lost it. But the algorithm is pretty fast. It's not crazy. It's just some group of computer scientists do it. One of my homework assignments, I made students create their own hash function. And it had to well distribute the data. And if not, they lost points. Oh, I got mad students on that one. Really good students are like someone just said, "Oh, I just tried this on a whim and it worked." And they were everyone, and someone would be trying for hours and days. Like, I'm still trying and I keep failing this test. It was really luck of the draw. So I dropped that. Matt, what are you talking about with that? I don't know if... So encrypting has nothing to do with hashing. Encrypting is 2 forms. There's public-private encryption and there's straight shared key encryption. encryption is more like saying, a very simple example. Take every letter, move it 2 letters forward. Just rotate it. All A's become C's, all B's become D's, all C's become E's, and so on. Is that easily undoable? Yes. So encryption is more of encryption is two-way. Whatever's been done, you can undo it. Hashing is not undoable, it's one way. All right, are we doing good so far? Questions on this? All right, let's give a brief idea of hash functions or hash tables, and we will end here.
We're going to do a participation code.
Should we do one right now?
Yeah.
All right, let's find 6 consecutive digits in the hash function.
There's no reason we can't use letters, is there?
Right here. 821227 is a participation code. 821227. It's guaranteed to be random.
Now let's hash that.
No, so you're joking. Like, now we can hash that. This is actually a strategy that password folks use. So LastPass, I use them. They're probably the #1 password repository system out in the world right now. They got hacked a couple years ago, and people worried because you need a master password to basically take care of the rest of your passwords. And if you had a very simple master password, they thought, like, could you start, like, let's say David used David for his master password. I always use you as bad examples of everything, David. I know, you should, because I'm picking on you really hard. He's smiling every time about it. So would it be their thought was, well, what if this hack does happen, and we have people using really easy master passwords? So what they did is they didn't just hash it once. They hashed it millions of times, and they stored that. So in order to generate a lookup table, it takes a computer, they said something like it takes a computer about 1 second to take a name or a password, hash it that many times, and then have the resulting hash to look up against. So if you wanted to generate a master lookup table, you would, if you just did diction, you would be able to do 1 a second. There's what, 86,400 seconds in a day. After 1 day, you'd have generated 86,000 possibilities. You'll pick off the easy ones, but the hard ones, you're never going to pick off.
Not enough time in the universe.
So hashing something over and over and over again is a smart strategy. Hashes are just a good general tool. It's like you go to a hardware store and you pick up a shovel or a screwdriver. Hash functions are that ubiquitous. All right. So now let's use. Yes.
Is there a way to know, like, how is hashed? Like you said, there was MD5 or 256 or 512. Is there any way to even know? Well, I guess it's 256 characters. Otherwise,
Yeah, that's why it's called SHA-256. It tells you how many bits are involved. That the output is 256 bits. SHA-1 though wasn't 1-bit output. It was more, but they now try to make the output representative of the name. All right, help me design a data structure. We're going to take, say, the last, just keep it simple. We're going to take the last digit. We're going to have 16 buckets. Help me design a data structure around 16 buckets to store things in. Does that make sense? I want to, again, nuclear blast happened. We can't ask anybody else. It's up to us. How do I make 16 buckets? Or how do I pull this off?
You make an array.
You have a tree. Hold on, we're going to just lay it all out. We do something with a tree. What's your tree idea?
You have one, then you can use nodes.
I have 16 buckets. How do I make a tree into 16 buckets?
Well, you can have one root node that points to 16 buckets, or that has pointers to 16 different buckets.
Okay, I mean, couldn't you just done an array at this point? and call this your pointer to the array? Yes, you can. All right, 4 branches of 4 could work, but you know, we're just going to do, I would just do an array of 16. That gets the job done. Let me see if I can actually draw out my array of 16. Try again. You could do that. I gotta draw 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Hey, that was pretty good. All right, so I have 16 buckets. And so you were gonna say for each of these buckets, you would give it a pointer to some other array, correct? Is that what you're getting at?
Or linked list.
What would you do? What would you like these secondary buckets to be? Would you want to make them arrays or linked lists, and why?
How much data? Are we
What would you think? What would you make them? An array or a linked list?
what kind of
Does
data?
it matter yet? Do you know?
It depends on what kind of data we put into it.
Any object. It's an array of those objects or a linked list of those objects.
I think a linked list would be
Yeah, I don't know, array, we're not changing the data, right?
I would put it in a linked list because we don't know how many items that we're adding or minusing to them. And an array would
You're saying what if we, let's say I make this bucket have only 4.
Yeah.
But as we start using this hash table more, we realize this bucket now has 20 items. So what do you do with an array?
Make it
You have to
about-
resize it. We know how much of a pain that is. What if we had linked lists?
Yeah, doesn't matter.
Now it depends on your application. If you need super fast lookups, but you're limited on bucket size, arrays are always fast. And if you're not going to be, if you're not going to be adding to your hash table, you just make it once and you're done. I would do arrays. But if I know I'm going to be adding or removing, I'd probably do linked lists.
So if
It really depends on the application.
So if we're making a one-time use that had, let's say that we have a grocery store.
Yes, and we're not going to add items to it, not going to remove items. We just have a giant list we want to throw in a hash table. I'd probably just use arrays here. Now there's one, you'd have to have a good feeling though. There might be a downside to arrays that you want to make sure that you can't guarantee that all buckets will be perfectly evenly distributed. So you might have to make one bucket, you have to make these buckets large enough to handle the worst possibility. So you might have some wasted space in that. But you gain speed because there are arrays.
Yeah.
Was there another hand that went up?
How would you know what your largest possible buckets?
All right, let's take students. We had 100,000 students. Let's say I split them up into 16 buckets. Okay? So how many per bucket? 6,250. Did you know that off the top of your head, or did you already compute it? You knew it? Way to go.
I would double that.
So you would double it, just to be safe. It's like, you know what? There maybe you go crazy. I mean, it's not likely one's going to go double. If it were me, I'd probably go to 9,000, 8,000, and then run it and see if it crashes.
What I'm saying, if you want to truly be safe, doubling it would make sure.
Yeah, doubling will probably get you there.
Or you can just do it by, like I said, you could just put it, you could just quarter the thing and just put an extra quarter amount on top or something.
Sure. I mean, it's really your call. If they're linked lists, you don't have to worry, but arrays are fast. A linked list with 6,000 nodes in it is a bit slower to look up. I mean, for one student at a time, it's fast, but we need to start thinking in terms of millions of hits, millions of times. So it's really your call. So we could do linked lists or we can do arrays. And if we were to do linked lists, I'll make my linked list go downwards here. Do we have a good data structure that should pull off what we want? Yes, so let's, for example, someone tell me the last digit of, let's say one of your W numbers hashes to a B. What do I do with that?
Put that in the.
I go to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B at 11. And I would then have to go down, and let's say you were already in there. I would have to go down and find some node that has a matching key in it. Does that make sense? If I find that matching key for the W number you supplied, I could say, hey, I found you, and I could return the data object. Does this get the job done? Does it go fast? It goes really fast. Is it expandable?
Yes.
Oh, yes, sorry. Yes.
Are you saying
Linked
yes
list-
because everybody else said yes,
No,
or?
I was initially thinking no because I was thinking arrays, but no, it is linked list. Yeah, it's fast.
If it fills up too much, then it gets slower, but.
It can. Let's No, I think that now would be a good point to end here. Next time, what I want to talk about is some of the how we would design this thing exactly. For example, I say you look up the key, but how do you exactly look up the key in that? How would this be designed? What would happen if your buckets fill up, but then you want to make your hash table wider? What do you do then? What if you have an operating system or you're working on some kind of computer system where you can't just make nodes on the fly? You don't have a heap. You can't just use new and delete. Or malloc and demalloc are free. How do you create a hash table without freely generated arrays? I want to pack it all in. And so we're talking about an array-based approach for hash tables, and start talking about, in fact, that would be time to start talking about the next assignment, depending on how this assignment goes. I tentatively gave it to Monday. We'll see how things look. I would not be surprised. Don't put it off, but this assignment it has a chance of getting pushed back to Wednesday, but it will be dependent on how many of you get it done. If 80% of you get it done or 90% done by Monday, we're not extending. But if 50% of you get it done by Monday, yeah, I extend.
I know what we're doing this weekend.
Just get it done. All right, other questions for me? All right, watch for the quiz that I'll be getting out the door. It'll be due in a week. Other than that, let's end here, and I'll come help you for lab time.